So that's the formulas which we got the last time. And now we'll do some derivatives, some integrals using these 3, maybe 4 formulas if you also take into account that antiderivative e to x equals to e to x plus c. As the first comment is going to be, if I want to find antiderivative of 3 to x. So let me try to address that situation. What I'm going to be doing is I'm going to use property that natural log is inverse function of e to x. So it means if I take e to the power ln of x, so it means I'm taking ln and then I'm taking e over it, exponential function, so they cancel each other, so at the end I'm going to get just x. So in particular, 3 equals to e to ln of 3. Okay. So now let's use that and let's substitute that expression for 3 into the derivative of 3 to x. So we wanted to find derivative of 3 to x, and 3 is equivalent to e to ln of 3, and then multiply by x. And then we'll do chain rule. Our inside function is going to be ln of 3 times x. Outside function is e to x, so we're going to get derivative inside function is going to be ln of 3. And derivative outside, e to the is e to the. And then you recall that e to the ln of 3 is just 3, so we're going to get ln of 3 times 3 to x. So that's going to be our answer for the derivative of 3 to x. So if you like, you also can write that as more general as a formula. And derivative a to x equals to a to x times natural log of a. And the proof will go exactly the same way as we did with 3. Just all that you have to do is just substitute a instead of 3. And don't forget, we always assume here that a is positive. If a is negative, then a to x make no sense because often x is going to be fraction with denominator, even denominator, so we're going to get like even roots. So we cannot do that. And also on the right side, if you look carefully, you have a natural log, and natural log is defined only for positive numbers. Okay, so that's maybe one more formula. We're not going to be seeing it often because most of the time we'll assume that our exponential functions are going to have base e and a natural base, at least for calculus. Now let's do a couple derivatives using natural log. Find the following derivatives. The following derivatives. Say ln of 1 plus x squared. We want to take its derivative. So here we have inside function u equals 1 plus x squared, outside ln u. So derivative inside will be 2x, derivative outside, derivative of natural log is 1 over u. So we can chain rule, so we're going to get 2x over 1 plus x squared. Natural log of sine x plus cosine x. And I want to take its derivative. Derivative of natural log is 1 over, right? Derivative of natural log is 1 over, we had it somewhere here. Okay. So derivative of natural log is 1 over argument. 1 over u as we did in the previous case. And derivative inside function, derivative sine is cosine, derivative cosine is negative sine. And we will write that as a big fraction, cosine x minus sine x plus cosine. That's going to be answer for B. Derivative of x cubed plus x squared plus x plus 1. Okay. So actually, I'm going to give you a minute or two to try to figure out what will be the derivative of that expression. Okay, let me try to catch up on you. So derivative outside function, derivative natural log is 1 over, and we keep this original argument, x cubed plus x squared plus x plus 1. And derivative inside function, derivative x cubed plus x squared plus x plus 1, it's straightforward. 3x squared plus 2x plus 1, if you like, plus 0. And the only thing which I'm going to do with this expression is I'm going to rewrite it as one big fraction. 3x squared plus 2x plus 1 divided by x cubed plus x squared plus x plus 1. Okay. And if you like, you probably already noticed the pattern. So the pattern is the following. So if you want to take derivative of ln of any expression here, then derivative of ln is 1 over, so we're going to write that expression. And derivative is inside is derivative is inside, right? So that's shortcut. So derivative of ln of f of x is going to be f prime derivative on top divided by the function. Okay. And that's exactly what you noticed. So for example, in the previous example, you see the derivative on top, you see the original function on board. Same way here, you see derivative on top, function on the board, argument of ln. Say ln of x squared plus e to x and its derivative over original argument, and on top its derivative. And when we're taking derivatives, of course, the rest of the rules will also follow. For example, product rule, quotient rule. Say, I will do example with product rule. If I want to do x squared times ln of cosine x, I'll do product rule. That's my scheme for product rule. And the first brackets, I'll put x squared. In the second, I'm going to put ln of cosine x. And then derivative of x squared is easy. Derivative of ln of cosine x is also easy. If we realize that we already did a bunch of those and we know the shortcut. So the final answer is going to look something like that. And the only thing which you can do here is maybe from a second fraction is to just take negative in front. So it will be easier to read, and maybe I will rewrite as one big fraction, but otherwise it's fine. Maybe to switch language of tangent, sine over cosine is tangent. I'm not sure, but that's one thing. That makes sense. Now let's do integrals. Let's do integrals. Let's do integrals. Okay, that's more interesting. Derivative is straightforward. So at least they're supposed to be straightforward. You do the rules, and then you do a little bit of algebra better. These integrals are a little bit more confusing. So basically, the only technique which you have so far is substitution, which kind of helps. So you either realize what immediately to do, or you do one small substitution, maybe a second substitution, and we proceed from there. Okay, so it's kind of ideal. So let's try. So say if you want to find integral of dx over 3x plus 7. So I'll do substitution u equals 3x plus 7. We find du, we find dx. I'm going to give you a minute or two to fill up the gaps. Okay. If I'm correct, you should be getting 1/3 integral du divided by u. Are you getting that? Okay, it looks like we're in good shape. Let me try to finish up. Okay, so if you want me to fill up the gaps, then du equals to 3 dx, because derivative of 3x plus 7 is 3. Then find dx, so du divided by 3. So we're going to get integral u on the bottom, and I will slide dx somewhere on the side. I'm going to slide it on the side, so we're going to get du over 3. So I'm going to slide du to the side, and then I will take 1/3 out, and that's how we're going to get that. And then we realize that is antiderivative of natural log of u. And then we'll do back substitution, and then we're going to be in good shape. Okay. X integral, x squared dx divided by 2x cubed plus 1. If you look at that expression, you basically know which substitution we want to do, 2x cubed plus 1. Again, find du, find dx, proceed with your substitution, get integral in terms of u. Okay, so let me try to catch up on you. So if I'm correct, we should be getting 1/6 u over u. Are you getting that? Derivative of 2x cubed plus 1 is 2 times 3 is 6, so 6x squared dx. Then we solve for dx, so du over 6x squared. So now we're going to substitute that. So we're going to get integral. Keep x squared. I'm going to slide dx to the side, right? So I'm going to slide dx to the side. I'm sliding it, so I'm writing du over 6x squared instead of dx. And instead 2x cubed plus 1, I'm going to write down du. And then I will reduce x squared and x squared. Then I realize 6 is a constant, 6 on the bottom, so 1/6 u over u. And then we dealt with that integral already a few times. So we're going to get 1/6 natural log of u plus c. So we're going to add 1/6 natural log of 2x cubed. Next integral looks a bit confusing. Tangent x dx. But it's not going to be too bad if we realize that our tangent is sine or cosine. And then we realize that we're going to be doing substitution similar to what we already did. So u equals 2. So here we have two options. We either do substitution sine or cosine. Sine is difficult as cosine, but keep in mind that cosine is on the bottom. So denominator is more difficult than numerator. So because of that, we're picking, for substitution, we're picking part from more complicated function, more difficult one. So u is supposed to be cosine. Okay. So try to proceed, find what du, find what dx, and eventually find integral in terms of u, and finish that. So if I'm correct, we should get negative du over u. So we should get negative ln of absolute value of u. So we get negative ln of cosine x. Just one small comment here is often the same answer, integral of tangent x dx, is going to be written as ln of secant x plus c. It's equivalent to what we have here because secant is 1 over cosine. And using the property of log, log of quotient equals to log of difference, difference of logs. So ln of 1 minus ln of cosine x plus c. Ln of 1 equals to 0, so we're going to get negative ln of cosine x. So our answer, which you got just a minute ago, and the answer which might be given to you in a book, in the textbook, are equivalent. So it's a matter of how you'll rather write it. So ln of secant x plus c for the value of antiderivative tangent x is kind of more standard, but I don't see much of a difference if you will write negative ln of cosine x.